Right, so this is the final presentations for the projects that students did for the C150, 259s and 159. They did research or projects on a particular school here, and mostly how to design green infrastructures to improve the school functions for water treatments or water harvestings or stormwater management. So they have 6 to 8 students here, and Imani is going to present first. Go ahead, Imani.
Awesome. Thanks so much. Hi, everybody. Our group is called Green Grads, and our project title is Ideal Parking Lot in Los Angeles, where we did a redesign at John R. Wooden High School. So Wooden High School is located in Reseda, California, which is in the San Fernando Valley, also in Los Angeles County. 95% of the students that attend this school are minorities, and 97% are economically disadvantaged. And our project is focused on the parking lot, which currently consists of gray infrastructure, which is primarily impervious surfaces. And the school's optimal location to redesign the parking lot has the goal of becoming a living laboratory. So the mission statement for Wooden High School, which is a continuation school, is that classes are personalized and we use a project-based holistic approach, focusing on social, emotional, and academic growth. And so we believe that green infrastructure instruction can supplement the existing outdoor education programs that are already existing at the school, which has a partnership with Kindred Spirits Care Farm, which is a current community partner with UCLA. So getting into the specific pollutants at our site, the pollutants that we focused on were heavy metals, which include copper, lead, and selenium. And then there's also indicator bacteria that's associated with pathogens in this area. And so we know that parking lots can accumulate heavy metals as well as debris, and also can accumulate polycyclic aromatic hydrocarbons from the motor fluids that come off of the cars. And so you can see from the graph on the right, or the map on the right, that the runoff will go into Aliso Creek and eventually empty into the Pacific Ocean by the Los Angeles River. And with that, I'll pass, and what we decided to do for our project to upgrade it are implement three BMPs. First, we did bioswells, then we did bioretention chamber, and we also added some solar panels. And with that, I'll pass it on to Steve to talk about the site's hydrology.
All right, thanks, Imani. So here's a picture of the drainage area for our site. Our proposed development has about 1 acre, and we assume that the runoff from the building's roof and parking lot drains to the north end of the lot. And right now, as is, the area is about 90% impervious, and the site's 85th percentile of storm depth is about 1 inch. And using this information, we calculated the peak runoff flow and volume, which ended up being about 0.32 CFS and about 3,000 cubic feet for the volume.
Now I will go over the bioswell BMP. So bioswells are channels with low-lying vegetation that collect and slowly convey stormwater runoff to a downstream stormwater quality control measure, storm drain system, or receiving water. We decided to place the bioswell in the back left corner of the parking lot, and its main purpose is to provide pre-treatment prior to the bioretention chamber. So for this sizing of the bioswell, we use the LA County Low Impact Development Manual, and we decided on a length of 117 feet and a width of 10 feet. The bioswell consists of the top layer being gravel, plants, and mulch, and the middle being 70% sandy loam and 30% medium sand. The bottom consists of gravel and an under drain that directs the water to the bioretention chamber.
So bioswales must be vegetated to provide adequate treatment of stormwater runoff. So native and adapted grasses are preferred because they generally require less fertilizer and maintenance and are more drought tolerant than, say, more exotic plants. So here's some suitable plants suggested by the LA County Drought Tolerant Gardens Handbook. There's some perennials here, some plants for ground cover, and some grasses. These are all designated for bioswale uses and use with sandy soils. So according to the Water Board cost estimating resources for various stormwater control measures, the total installation cost for the bioswale that we designed is approximately $9,000. And then and the additional yearly cost of maintenance, including mowing and cleanup tasks, are estimated to be around $500 per year. And this is kind of what the bioswales would look like from the top. So now a bioretention.
Okay, so the bioretention basin will be placed on the northwest part of the lot, and it will come after the bioswale. And it's a volume-based BMP, so it means that there's water that's allowed to pond on site, and pollutants are removed by the vegetation that's placed in the basin, as well as the filtration media that's used. And the basin for our site ended up being around 60 feet long and 30 feet wide. And in a storm event, we'll have around 1.5 feet of ponding depth.
So for our bioretention design, we actually modeled it off another system, which was featured in a paper in 2011. That's the Paul Matthews bioretention system in New Zealand. And the substrates that were chosen for the infiltration system were chosen to have high metal removal and also high permeability. And so you have a diagram on the left of the various layers that we went with. So to start at the top, you have the drought tolerant vegetation, one half foot of compost mulch below that. And then you have a foot of lawn mix, 3 feet of subsoil, and then finally 1 foot of coarse sand at the bottom. And here's a table of the actual filtration performance for that Paul Matthews system featured in the paper. And what you can see is that overall, it had a pretty high median filtration performance for the total suspended solid, the total lead, and the total and dissolved zinc. For all of those materials, or for all of those pollutants, they had over 90% filtration efficiency. And it was just the dissolved copper, which had a negative performance. And that's possibly due to slow release fungicides that are used in the potting mix, which could actually release dissolved copper when water passes through the system. But overall, very high filtration performance. As far as installation and maintenance costs go, it's definitely more expensive than a bioswale system. For the installation, it's priced on a per cubic foot basis, and the size of our system comes out to about 160,000 for the installation. And similarly for the maintenance, it's 14,000. However, there are noticeable beneficial uses to having the system in place, where the stormwater capture can be used to irrigate the local farm on the school campus, or it could be used to clean the solar panels on the solar canopy, or to simply recharge the groundwater system below.
Okay, so now I'm going to talk about our solar system. So we decided to put the solar panels in the northwest parking lot and rooftops, just to have the optimal orientation for them. So the solar panels in the carport structure will provide shade for cars and pedestrians, generate clean energy, and prevent rainfall from landing in the parking lot and then picking up those harmful pollutants we were talking about. And then the carports can have gutters attached to them that will direct the water towards the bioswales and bioretention systems. So we used a software called Helioscope to estimate the sizing of the solar system. So you can see the layout. We have the carports in the parking lot, and then we picked 2 different rooftops to have more solar just to increase the production for the school. So you can see the annual production broken down monthly on the right in that diagram with a total of about 130 megawatt hours produced per year. And then, so for the overall cost, it's about $450,000, and then maintenance is included for 10 years, and then annual cleaning costs of about $1,000, using about 1,800 liters of water per year. So factoring in all these costs, it had about a 14-year payback period. So past that point, the school will be saving money on their electricity bills. And then just to wrap up our overall design and summarize, our bioswale system will reduce from 83 to 92% of total suspended solids, 67% of lead, 46% of copper, 63% aluminum and dissolved zinc, and then 75% of oil and grease. And then it'll also add to the site aesthetics with all the plants. Our bioretention system will increase stormwater harvesting for the school and allow them to have more of a reuse program of about 3,000 cubic feet per year. This will help make the school more self-reliant and increase their ability for groundwater recharge if they don't use all the water. And it also will help treat nutrients before entering the creek nearby. And then our solar panels will save the school about $50,000 annually on their electricity bill and help redirect stormwater to the different green infrastructure items that we chose. And that is it, if anyone has any questions.
Very good presentations, right on time, 12 minutes exactly. You guys practice well. I really like the presentations, and I've seen the slides, so you presented also well. First, any questions from students? I have a few questions. If you keep going back to the slides, there is a table that you said that the dissolved coppers are being released. I think removal capacity. No, keep going back. Keep going back. Yes. So it says that filtration performance. Is this the based on the concentration? For instance, you write 30 and 3, so that means 90% are removed. So this is based on the concentration, right?
Yes, this is based on the median concentration.
Okay. And do you know how long they have been monitoring the systems? Because normally it's everything removed very well, because you write the dissolved copper had higher output concentration may have come from slow release fungicides. So that means if they don't have fungicides, do you think that they would have better removals?
Yeah, I think that would be the case, although they don't know for sure if the fungicides are the reason for the higher dissolved copper. I think that was just their guess at what it could be coming from.
The reason is usually zincs are very difficult to remove. Coppers are much easier. They bind with organics. So when I see that coppers has lower removal than zinc, it indicates that something is there that release copper. So that's probably the reason they write. Fungicides may be the reason. But it's interesting data. So you can check whether this is something they monitor for many years or this is just one-time monitoring, because things will over time will improve because fungicides are replaced.
Yeah, I think it was definitely monitored over definitely a span of time. There were various different measurements, but.
And if you go back, there's another place I go to slides. Keep going back. I'll tell you one place. Keep going. Yes, so this is the one. So the next one, the one where this is the one. So the high school is right there. Is this I see that you create this map where you say this is a replacement for, solar panel is not going to change the parking arrangement, right? But any other places where you dig soils or replace it, with something else, you are going to take away some parking spot. So how much space you are going to take away? So something that you should write that in your report, that this much impervious surface is replaced by this much permeable surface. And that means, you have to account for how much parking spot that would be. What incentive schools would do to, because they lose some parking spot, it may be useful for them. So at least to discuss about that is important.
I think if you look on the slide before this, yeah, you can see that they have like kind of like just grass on the sides. So most of the bioswale and bioretention would be like replacing that area. So it didn't really change the parking lot size.
That's good. That's good. I think I see the marks not too close to that spot. So that's good. Yeah. So this is the entire school. If you the entire area is school, it has some basketball and some other places there. Yeah, this is a good spot to actually use as a model systems. And another thing to think about is um, the school, which people they serve, where they are coming from, and how to integrate this design into their learning, right? So that something is not necessarily part of the design, but you can integrate that as a discussion. Okay, I think that's a very good presentation, and I'll have just few comments for the presentation. If you imagine this is something you'll present to the in the industry. Usually what it does, the way you did it is very much similar to a poster. So if you have a poster, somebody is going to just come here, you are not here, I can read the question, read the informations, and then I can also get the informations. So when you were presenting, I was not reading what you wrote, I was listening to you more, right? So that means, every time you have more pictures or large pictures, I can see through things that you are telling. And because a Zoom presentation is just easier to write on your notes or something where you also understand it and fill the entire slide with the pictures. That way we are less distracted with reading the slides. And another thing is, like, for instance, let's say now what this picture about. Your picture says that it's located in Los Angeles, and that top right corner, that's the place that says that. And then it says 95% of the students are minority, 97% economically disadvantaged. Even though you are making that claim, there is no way for us to see that in this picture, right? So even you just present that first bullet point and put this picture and then move to another slides where you just put a pictures of students, just visually it shows that, these are the students, or it doesn't have to be that students, you can just visually how you can link with what you're saying. It takes the same time, but it makes a big impact on how listener or the readers or the viewer perceive your message. So every time you see like four message, like 4 bullet points, think of how you can break into 4 different slides and put some kind of pictures that kind of represent what you're saying. And that just makes it easier for viewer. Other than that, as I said, you say the same thing, but you don't have to stay in the same slide. So that's all I had comments. But any other questions from students? Yeah, it's a pretty good presentation. So I would stop recording now.